right, this is question 16.29. Wants to know the magnitude of the electric field if you have charges at the corner, charges at the corner of a square. So let's say the point here, we'll call it O. So all the charges are equal. Everybody has different numbers in mastering, so I'm just going to call each of these Q. And I'll call the side here L. It's a square, so all the sides are the same length, except for the diagonal here, which is radical 2L. If you're not sure why, side squared, if you add those two and then square root it, you get radical 2L. So if we look at, again, the field at this location right here, what is the E field here? It's going to be due to this charge, and this charge. Each of those contributes to the field. So if we just go in order, starting with this one, you're going to have a field that goes in that direction. Let's label that 1, this one 2, and this one 3. My drawing's getting a little noisy, but whatever. So that's E1. E2 is going to be that. It'll be at a 45-degree angle. And E3 will be downward like that. Again, this is a positive charge. If we put a positive test charge here, each of these charges cause a repulsive field. Now, how to get the net field? E net. What you have to do is you have to sum all the individual fields. So it's going to be E1 plus E2 plus plus E3. But these are vectors that we're summing, so we can't just say 1 plus 2 plus 3 equals 6. Whatever the magnitudes are, we have to do the vector addition. Now, in this case, normally what we would do is we would break this vector into its x and y components. But I think it's actually easier to find the resultant of E1 plus E3, because the fact that they're equal, and the reason why they're equal is it's KQ over R squared is how you calculate E. E1 is going to be the same K, the same Q, and the same distance. Right, that squared is supposed to be there. So I think it's easier to, like I said, sum these two together, so this plus this, because what that will give you is this plus this will give you this, and this will be at a 45-degree angle, which is what this one is right here. So then we can simply just add this and this together. Hopefully that makes sense. So another shortcut, if E1 and E3 are both equal, like they are, the resultant, this E field vector, resultant vector right here, just like the diagonal was radical 2L, which is the resultant of the two sides, if you want to look at it that way, this resultant here is just radical 2 times whatever the sides are, or that the vectors are, which is what E1 and E3 are. So it's just KQ over R squared. So that's E1 plus E3, and it's along E2, this one right here. So on a new sheet of paper, what you'll see is now we have E2, and we want to add E1 plus E2, E3 to it. So we need to know what E2 is. We just found these. I think we said it was radical 2 KQ over R squared. E2 is KQ over R squared, and R squared, I go back a slide, R squared is this diagonal, that's the value for R. So let me go forward. So this is going to be radical 2L squared. When we get that, all we're going to do is, like I said, add it to this. So plus E2. So it looks like your answer is going to be kq over 2 L squared plus radical 2 kq over r squared, which equals kq, whoops, this r is L, and if I go back to this page, it's the side length, so it's either this L or this L. Again, very busy, so we can cross off the r and make that be L. So it looks like a common factor is kq over L squared, and we have 1/2 plus radical 2. So again, your values for L vary, values for Q vary. Make sure you put these in coulombs, not microcoulombs. Make sure you put L in meters, not centimeters. And you do the math, you'll get the right answer.